Here's a question that sounds like it shouldn't have a sensible answer. If a massive sheet of ice in Antarctica melts entirely, pouring trillions of gallons of water into the world's oceans, which coastline gets hit hardest? Most people would say whichever coastline sits closest to the melting ice, the same intuition you'd apply to almost anything else in physics. The nearer you are to a source, the stronger the effect. NASA scientists will tell you that intuition is completely wrong. According to their own published research, when West Antarctica's ice eventually melts, the water will raise sea levels more in Los Angeles and Miami than it will in Rio de Janeiro, even though Brazil sits thousands of miles closer to the source than the United States does. That's not a typo, and it's not an approximation. It's a real, measured, physically explainable phenomenon, and it's about to become considerably more relevant because the last natural break holding back one of Antarctica's most dangerous glaciers is expected to fail sometime this year. Let's follow this mystery all the way down, from a fracturing wall of ice at the bottom of the planet to exactly why the coastlines of the United States are the ones that should be paying the closest attention. Subscribe to the channel before we get into this, because this is exactly the kind of counterintuitive scientific mystery I love digging into. The ones where the answer runs directly against what your gut instinct tells you should be true. Let's start at the source of the mystery, deep in West Antarctica, at a glacier scientists have nicknamed the Doomsday Glacier. Thwaites Glacier is genuinely massive, comparable in size to the entire island of Britain, or by some comparisons, to the state of Florida, and it's been losing ice at an accelerating rate since the 1980s, retreating roughly 12 miles since 1992 alone. It already accounts for approximately 4% of all global sea level rise happening right now from this single glacier alone. If Thwaites were to fully collapse, scientists estimate global sea levels would rise by roughly 26 inches, enough on its own to flood coastal communities worldwide. And Thwaites isn't just dangerous in isolation, it functions as a key structural pillar for the broader West Antarctic ice sheet, meaning its collapse would remove support currently helping to hold back considerably more ice behind it. If the entire West Antarctic ice sheet eventually followed, the British Antarctic Survey estimates global sea levels would climb by an almost unimaginable 10.8 feet. That full collapse remains a process scientists expect to unfold across centuries rather than years or even decades. But right now in 2026, a considerably more immediate chapter of the story is reaching its climax, and it centers on a specific floating extension of ice attached to Thwaites' seaward edge called the Thwaites Eastern Ice Shelf. This shelf, roughly the size of Greater London and about 350 meters thick, has been performing a function. Researchers describe using a genuinely evocative comparison, acting as a doorstop, wedged against the outward flow of ice, physically slowing down how quickly the glacier behind it can reach the sea. It's held partly in place by an underwater ridge on the ocean floor, an anchor point that's given the shelf just enough structural leverage to meaningfully restrain one of the most unstable glaciers on the entire continent. Now that doorstop is failing, and the evidence comes from satellite images tracking exactly how the shelf has been changing over time. Researchers from the University of Manitoba analyzed 2 full decades of satellite data, from 2002 through 2022, and found the shelf has experienced progressive fracturing around a specific shear zone sitting upstream of its anchor point, gradually compromising its structural integrity year after year. The total combined length of visible fractures across the shelf grew from roughly 100 miles to more than 200 miles over that period. And here's a genuinely strange, almost forensic detail buried in that data. While the total fracture length was climbing, the average length of any individual fracture actually decreased, a pattern researchers interpret as evidence of major new stresses spreading across the entire shelf structure rather than just a handful of large cracks slowly widening on their own. It's the kind of clue a detective might flag as evidence that something systemic is happening beneath the surface, rather than one isolated point of failure. Robert Larder, a marine geophysicist at the British Antarctic Survey who runs the UK arm of the Science Coordination Office at the International Thwaites Glacier Collaboration, has spent years tracking exactly this system, and he's been direct in his most recent assessments. The last remaining piece of ice shelf in front of the glacier is very likely to break up in 2026, he said, adding a genuinely honest scientific caveat immediately afterward. We don't know quite how this ice shelf is going to break up, but it's definitely going to go. Larder has compared the challenge of predicting the exact moment of collapse to forecasting an earthquake. Researchers can watch the strain accumulating in real time, tracking every new fracture through satellite imagery, but pinpointing the precise instant. The entire system finally gives way, remains genuinely beyond current scientific capability. The numbers behind exactly how fast this system is deteriorating right now are genuinely startling once you see them laid out. A researcher named Wild, cited in recent coverage of this unfolding event, found that the shelf's own flow speed increased more than threefold between January 2020 and January 2026, climbing past 2,000 meters per year, with even further acceleration observed in the most recent months. In an upcoming study, Wild and colleagues also found that the glacier ice sitting behind the shelf, the ice, this entire structure exists specifically to restrain, sped up by roughly 33% over that same 6-year window. That's the mystery's first genuine clue about what's actually at stake here. The shelf doesn't need to fully collapse to start losing its grip. It's already losing its restraining power right now, measurably, in real time, well before its final structural failure even occurs. Beneath the surface, researchers have identified something even stranger happening on a timescale of mere hours and days rather than years. Warm ocean water doesn't simply sit still and gradually erode the ice from below in a smooth, predictable way. Researchers have tracked swirling eddies of water, some measuring up to 6 miles across, spinning and burrowing directly underneath these ice shelves. And, as they interact with the ice, they've identified a genuine feedback loop. New cold water released from the melting shelf mixing with warmer, saltier ocean water attacking it from beneath. A cycle that actively sustains and even accelerates the melting process once it's fully established. It's a genuinely unsettling image, an enormous, ancient wall of ice being undermined not by a single steady force, but by an active, self-reinforcing churn happening in complete darkness, thousands of feet beneath the surface, invisible to anyone except the researchers, piecing the story together, one satellite pass and one measurement at a time. So here's where the real mystery of this story actually begins, because everything we've just walked through explains what's happening to the ice itself. It doesn't yet explain why the United States, of all places on Earth, stands to be hit hardest by the eventual consequences. And the answer to that question requires leaving Antarctica entirely and turning instead to a piece of physics most people have genuinely never encountered, even though it's been understood by scientists for well over a decade. Picture melting ice the way almost everyone instinctively does. Water filling a bathtub evenly, the level rising the same amount everywhere at once. That picture, according to NASA's own research, is simply wrong. The actual pattern is shaped by gravity, by the rotation of the Earth itself, and by the way the solid planet physically deforms as enormous quantities of mass shift from one location to another. Scientists call the resulting pattern a sea level fingerprint, and once you understand the mechanism behind it, the entire mystery of why distant American coastlines face a disproportionate threat suddenly makes complete physical sense. Here's the mechanism. An ice sheet as genuinely massive as West Antarctica's exerts real measurable gravitational pull on the ocean water surrounding it, attracting seawater toward it in a way that's mechanically similar to how the moon's gravity pulls on Earth's oceans to generate our tides. As that ice sheet loses mass, that gravitational pull weakens correspondingly, and the seawater previously drawn toward it begins redistributing away, freed from an attraction that's no longer as strong as it once was. That produces an almost paradoxical outcome. Sea levels actually falling in the immediate vicinity of the melting ice sheet itself, while rising considerably more than the global average, in locations positioned much farther away, specifically because that redistributed water has to go somewhere, and gravity, rotation, and the solid Earth's own response determine exactly where it ends up piling up. NASA scientists first confirmed this exact pattern using satellite data from the Gravity Recovery and Climate Experiment mission, and Jerry Mitrovica of Harvard University, working alongside Mark Temessier of the National Oceanography Center in Liverpool, calculated precisely how this fingerprint plays out for each of the world's major ice sheets individually, publishing foundational findings in the journal Science back in 2009, and refining that work considerably in the years since. Their conclusion is exactly the counterintuitive answer we open this entire story with. Water freed from West Antarctica's weakening gravitational grip travels clear across the equator and ends up raising sea levels more in Los Angeles and Miami than in Rio de Janeiro, despite Brazil sitting thousands of miles closer to the actual source of the melting. I want you to genuinely sit with how strange that is, because it inverts almost every intuitive assumption people carry about how a distant environmental disaster should distribute its consequences. The closer you'd expect to be in danger, the coastlines of South America, Africa, and the Southern Hemisphere generally, sitting geographically nearest to Antarctica, actually experience some of the smallest relative increases, in some cases even seeing local sea levels drop as the ice sheet's gravitational pull on nearby water weakens. Meanwhile, the United States, separated from Antarctica by an entire hemisphere, sits directly in the path of where that redistributed water is physically destined to accumulate. The specific numbers behind this fingerprint effect are genuinely worth understanding because they turn an abstract physics concept into something concretely relevant to millions of actual people. NASA's research has already found that observed sea level rise along parts of the U.S. East Coast has been running 2 to 3 times the global average rate, a disparity already measurable today, well before any full-scale collapse of West Antarctica has even occurred. Modeling. The specific scenario where the Amundsen Sea sector of West Antarctica, the exact sector containing Thwaites Glacier, is completely gone. NASA's research found that while global sea levels would rise by roughly 4 feet on average, the east coast of the United States would see an additional 14 to 15 inches stacked directly on top of that already substantial global figure. The National Snow and Ice Data Center's own regional breakdown finds the single highest projected impact anywhere in the world falling specifically on the U.S. Gulf Coast, projected at 14 to 18 inches above the global average, with the East Coast close behind at 10 to 14 inches above baseline. So let's bring this mystery all the way back together, because I think the full arc of this story is genuinely one of the more fascinating pieces of climate science currently unfolding anywhere on the planet. Thousands of miles from any American shoreline, a wall of ice the size of a major city is currently fracturing along its anchor points, its restraining power already measurably weakening even before its final collapse. Driven by warm ocean water attacking it from below in a self-reinforcing cycle, researchers are only beginning to fully map. And through a mechanism rooted in gravity itself, the exact same physics responsible for the tides washing onto every beach on Earth, the ultimate consequences of that distant, invisible collapse are destined to land disproportionately, not on the coastlines sitting closest to the source, but on the shores of a country separated from Antarctica by nearly the entire diameter of the planet. That's genuinely the kind of story that reminds you how deeply interconnected this planet actually is, in ways that rarely announce themselves through simple, intuitive cause and effect. A doorstop of ice, failing in one of the most remote, least visited places on Earth, and a family building a home along the Gulf Coast of the United States, connected not by proximity, not by any direct, visible relationship, but by the quiet, relentless physics of gravity working exactly the way it's worked since the Earth first formed, simply waiting for enough mass to shift for its consequences to finally become visible along a shoreline thousands of miles away. If you live anywhere along the U.S. East Coast or Gulf Coast, I think this story is worth genuinely internalizing, not as a source of panic, since the broader collapse this shelf's failure connects to is still expected to unfold over decades to centuries, but as a piece of long-term context worth understanding, as you think about where you live, how your community plans its coastal infrastructure, and how seriously local and regional flood risk assessments account for a disparity in sea level rise that NASA's own scientists have been documenting for well over a decade now. I'll be following this story closely as the Thwaites Eastern Ice Shelf's breakup continues unfolding, watching for the moment researchers confirm the shelf has actually detached, and for whatever new satellite evidence emerges about exactly how much faster the glacier behind it accelerates once that final piece of restraint is finally gone. Subscribe so you don't miss that update, and drop a comment below if you'd ever heard of this sea level fingerprint effect before today, or if this is the first time you're learning that a glacier collapsing on the opposite side of the planet could genuinely matter more to your own coastline than it does to countries sitting right next door to Antarctica itself. I read every one of these, and I think a mystery this counterintuitive genuinely deserves that kind of shared reflection. Stay curious about the invisible physics connecting the far corners of this planet to the shore right outside your own window, and I will see you in the next one.